So, now that we have laid down the foundations, we can actually start to work. So let's look at the first application here, which is a multi-level vector autoregressive of order 1 model. And the data I'm using here come from a study that was run at the MPI Institute in Berlin 10 years ago, and is referred to as the Cogito study. And they were interested in aging, and so they had 2 samples. They had a younger sample of individuals, I have to see, yeah, between age 20 and 31, and an older sample between ages 65 to 80. First sample had 101 individuals, second one 103. And they had about 100 daily measurements. And they actually, because they were interested not only in self-report of affect, but also in cognitive functioning and learning and those kind of things, they had these people come to the laboratory on each occasion. So they had people come to the lab for 100 days. It's like so impressive. It's like, yeah, I don't know. The people were there, and then they were doing all these cognitive tests and then also filling out questionnaires about, for instance, their positive and negative affect. And that's the variables that I'm focusing on here. Now, what is fundamental to doing DSEM in Mplus is a decomposition into different parts. And here I will only focus on 2 parts, and later on a 3rd part will be added, but for now we're just 2 parts. And so we have positive affect and negative affect of individual I at occasion t, and it's decomposed into 2 parts. A between part, which we call mu subscript pa I. So it's the mean of positive affect for individual I. It does not have a subscript t because it's the mean of the person over time. So it does not vary over time anymore. And we also have a mean for negative affect. And then we have this second part here with the superscript w to indicate it's the within person part. So it's the individual deviation, temporal deviation at occasion t from the own person's mean. So we can think of this as the trait score of a person over time. And then the other part is the state part. It's like at this occasion you deviate from it a little, and then this varies over time. So the mu's are the individual means, sometimes referred to as the baseline. Although that sounds like that's something at the beginning only, but it's like the trait score. Also referred to as equilibrium, so it's the preferred state to be in a way. So it's for the between person part in the model. And then there's these temporal deviations within person, so it's the within person centered part. You can subtract the person's mean or the cluster mean from the score, and then you get this part here. So here we see 2 hypothetical sequences of individuals, and we see that the first individual has a higher mean than the second one, and then the deviations from the individual's mean, that would be the within person part. And we see that the within person part has a different structure for the first person than for the second person. We see second person has more variability, but also a little bit more structure in it. Well, it's sort of, if you're experienced. Sorry. If you created the data, I should say. All right, that's another form of experience. So then, one thing you can look at, of course, is intraclass correlation. So it's how much variance is there at the between person level in comparison to the total variance, and the total variance is the sum of within and between. And so I do this here for positive affect in both samples and then negative affect in both samples. We see that the middle bar is higher than the last bar, so the between person variance is larger than the within person variance on average. And that's also what you see when you look at the intraclass correlations. they're all pretty high. So that's just a descriptive way of looking at your data. The model we're running is here. So this is one way to represent the model. We had many emails going back and forth, you know, when we were developing this on how to best represent these models. Try to do it in one picture, basically, which is doable when you have univariate models, but for a bivariate model, it doesn't really work anymore. So this is a bit of a multi-dimensional picture. So you will see the one-dimensional picture. Well, one-dimensional sounds bad, but the picture in which it's all in one picture. You can see it in the manual, but then there's other pictures representing the more complex models. Here what we see is there is a decomposition. So that's what I showed, the decomposition into the between-person part and the within-person part. And then I have a within-person part here at the top and a between-person part at the bottom. So let's focus at the within-person part. That's where we have the vector autoregressive model. So I regress positive affect centered within person, so that's the W, and negative affect at occasion T on the two scores at the preceding occasion, so the preceding day. So we have the autoregressions here, and then we have the cross regressions crossing. Yeah. The black circles imply that these regression coefficients can be different across individuals. So these are random slopes. They have different values for different individuals, quantitative differences in the dynamics. And black circles become open circles at the between-person level. So that's why we have the phi and n. It's the autoregressive parameter for negative affect. And it has different values for different individuals. And we can correlate it, for instance, with the individual's mean on negative affect, which comes from the decomposition here. And the same is true for the other lagged parameters. So we have the 4 random effects for the random slopes, and then 2 random effects, which are the 2 means from the decomposition. And all of them are allowed to be correlated here. And then here we have the innovations, which will have variances and a covariance, and that's at the within-person level. Doing the same thing, but now with formulas, we get the within-person model, positive and negative affect, both regressed on positive and negative affect at the preceding occasion, so t minus 1, plus a residual. The phi pp and phi nn are the autoregressive parameters, inertia or carryover or regulatory weakness. Phi pn and phi np are the cross-legged parameters, so phi pn is going to positive affect coming from negative affect. And it's referred to sometimes also as spillover, spilling over from one area into another. And then we have the zetas. These are the innovations or residuals, disturbances, etc. It's like everything that is not accounted for by including the previous measurement as a predictor. So the parameters that are being estimated at this level are the variances of the innovations, which I refer to as theta 11 and theta 22 here, and the covariance between the two. And one thing that's important to realize is that the zetas, they are not measurement error. So they're not just random measurement error. They are innovations, or they're sometimes referred to as dynamic error, because they affect, this affects the current occasion, but then at the next occasion, the current occasion is over here, right? So it's when we, oops, not sure if it's, yeah, it doesn't help this picture. So it's like you have this process, it's affecting a certain occasion, and then it's this occasion is then the predictor of the next occasion. So the residual is also ending up there. So that's why it's referred to as dynamic error, whereas measurement error would only affect a single occasion and not subsequent occasions. So it's not measurement error, it's everything that affects the process we're studying, and that is carried forward. So at the within-person level, we now have 3 parameters. The between-person level, we have those 6 random effects, the 2 means, and then the 4 regression coefficients or slopes. We have their means, so these would be referred to as the fixed effects, denoted here with gammas, and then individual deviations from these. So that's these 6 terms here, for which we are going to have a covariance matrix. So this means here we have 6 fixed effects, that's the gammas. Then we have 6 variances, it's the diagonal of the covariance matrix of those U's. And then 15 covariances, plus the 3 parameters at the within person level. And if I did it right, I think this is 30 parameters in total. I'm really bad at this, but yeah. Yes, because we have 6 plus 6 plus 3 plus 15. So we started out with 2 variables. Now we have 16 parameters. Now that might give you an awkward feeling, like, should we be doing some sort of data reduction, right? Neil and Ram pointed out to me that another way of looking at this is saying, well, I started with a data box or a data matrix of dimensions 100 days, 100 people, 2 variables. And now I've reduced this to 30 parameters. You know, that sounds much better. Yeah? And it's important to realize that the cases are not independent here. It's not, I mean, the individuals are independent. So in that dimension, we have independent observations. But within a person, the observations are not independent. So there is more information there. And that's what we're trying to account for with those lagged parameters and with separating within and between. So how do we do it in Mplus? Well, we have the data in long format. So similar to what I showed before, but we don't have to create the lagged predictors ourselves. That's something that Mplus is going to do for us. So we just need the data in long format. So here, I would have a variable that's the ID, so the person. I should have a variable that indicates what measurement occasion it is. And then I have the 2 variables, positive affect and negative affect. And that's it. So just need a data set with those 4 variables. So each record is a case, or sorry, is a time point within a person. And so we have multiple records per person. And this is how we do it. So here I have the variable commands. There's more variables, as you can see in the data set. But over here, I'm indicating I'm just going to use daily positive affect and daily negative affect, those 2 variables. There is a cluster variable ID, so that's to specify the different individuals. I indicate there's a missing value code, minus 999. Then I use this command here, lagged. And I tell Mplus I want to have lagged versions of those 2 variables, and please lag them by just 1. Right? So that's what the 1 here stands for. So it's going to be yesterday's positive affect and yesterday's negative affect. And then I have the t interval variable. So that's the session date, as you can see. So this is, the people came to the lab to do this. They didn't come on weekends. And sometimes they didn't come because they were ill or busy or on a vacation. So not all the observations are just 1 day apart. So we want to account for this when we do the analysis, because we know that lagged relationships depend on the interval between the observations. If I have observations that are closer together, the autoregression will be higher than when the observations are further apart. And for cross-lagged relationships, it actually might play out differently. Like the effect might be stronger at larger legs than at shorter legs for some interval and then decreases again. So we want to take the interval into account. And I'm going to explain this very briefly here. Bengt will be explaining more about this. I think he's practicing it now. Tiomir will be explaining it tomorrow. So you will get different explanations of the same thing, and hopefully, one of them will really click for you. What we have, this session date, is just telling how many dates, basically, since the beginning of the study is this. So suppose you start measuring on Monday, then you have like 1, 2, 3, 4, 5 from Monday to Friday. 6 and 7 are missing, and then the next one gets score 8. You know, it's the 8th day since the beginning. What I'm telling Mplus here is to use an interval of 1 for this variable. And with daily measurements, it's very easy to decide what interval to use. It's typically going to be 1. For ESM, it's going to be more complex. So then you have to decide whether you want to have it in minutes or in hours or 1.5 hours. But for daily measurements, it's easy. It's just 1. And what it's doing is that Mplus is looking like, OK, I see this variable 1, 2, 3, 4, 5, and then 8. So 7 and 6 are missing. And I'm going to just enter missing records in between, so that all the new records that you have are equally spaced in time. We're not creating new observations, but we're taking into account that the intervals differ. So we choose a time grid here. The grid is 1 day. This is the size of 1 day. And it's aligning the measurements in this grid. All right. And then the analysis command, type is 2-level random. So we're going to have a 2-level model. So that's with the decomposition into within and between. Random, because I also want to have the random slopes, the random lagged parameters. Estimator is Bayes. DSEM is all in Bayesian statistics. So there's no choice here. Not yet, anyways. I'm using 2 processors because that makes it go faster. Actually, because Bengt told me to, but yeah. B iter is saying I want to have, and then 5,000 here, is saying I want to have at least 5,000 iterations of Bayesian estimation. Bengt will explain more about Bayesian estimation, so I'm going to skip over that, but this seemed a good number for this particular problem. And thin is 10 is meaning that I'm only going to save 1 in 10 iterations. But again, Bengt will say more about that later.
May I ask 2 brief questions on the output?
Do you mind that one thing I forgot to mention, if you can hold the questions to a special period?
Okay.
We'll have
Yep.
15 minutes at the end. Thank you.
Right. Are we getting close to those 15 minutes, actually?
You can take another 15.
Oh, good. Right. He's so generous, isn't he? So this is... What, did you make a face? Oh, I'll watch it on the video. It's being recorded, you know that. So this is how we specify the model. So we have the model, we have a within part and a between part. So at the within part, we're going to specify the lagged relationships. And as you might remember, there's 4 lagged relationships, 2 autoregressive ones and 2 cross-lagged ones. And that's what we specify here. So I specify regress positive affect on positive affect at the previous day. So this %1 implies it's the lagged variable. And we created the lagged variable in the variable statement here. So we had the lagged. I want to have it at lag 1, and that's what I'm referring to here with the %1. So a daily positive affect on daily positive affect yesterday, daily positive affect on daily negative affect yesterday, and then the same thing for negative affect. So we have the autoregression here, and then the 2 cross regressions in the middle. So I call it P underscore PP. So that's the phi parameter for positive affect to positive affect. And this one is the phi parameter for positive affect coming from negative affect. So positive regressed on negative, negative regressed on positive, and negative on negative. You can give them other names if you like. You know, you can call them John, Pete, and so on, or whatever. Or S1 and S2 and S3. That's, I think, what Bengt prefers. So these are names that we give to those random slopes, those black dots in the picture. So these become variables then at the between person level. So that's what we see here. Between person level, I have those variables. And of course, the 2 means, they come from the decomposition. That's part of the DSEM approach when we do multi-level or 2 level. It will always be there. So here I'm just saying I want everything to be correlated with everything. That's what I'm saying here. The output, I asked for the Tech 1 output. I'm a big fan of the Tech 1 output. Asked for Tech 8 because Bengt told me to. And I asked for standardized results, as I will explain later why I'm doing this. There's also some plot options. I will say more about this later on. And this is what the results look like. So what we see over here is the results for the within-person part. As you might recall, at the within-person level, we only estimate the 2 innovation variances and the covariance between the 2. I refer to them as theta 1,1, theta 2,2, and theta 2,1 in the slides. So here we have the covariance between the innovations. So it's not between the variables, but only the residual parts of those variables. And then the residual variances. I don't think this is very interesting. Yeah. Then we go to the between-person part, and I skipped the first part of this, so that's why we have the ... here. I will come back to this later. So that's with all the with statements, all the covariances. But what I'm focusing on here first is the means and the variances. So as you might recall, so we have 6 latent variables or random effects at level 2 that are all allowed to be correlated. They all have a mean. That's what I was referring to as the gammas, fixed effects. And that's actually this, what we see over here. These are the gammas, or the fixed effects. And we can see that all of them are different from 0. So we can see, for the means maybe that's not such a big surprise, but we can see that all the lagged effects, on average, have a mean that differs from 0. So both the autoregressive ones and the cross-lagged regressions. And we also see the variances. So these are the random effects, and all of them are also getting an asterisk to indicate that they differ from 0. What are we seeing here? Actually, we see the point estimate in the first column. So that's your parameter estimate. The posterior standard deviation, which is, I don't know if I can say this, but sort of like the Bayesian equivalent of a standard error. That's like very slippery slope where I'm at here. There's a one-tailed p-value. That I don't really look at. There is this 95% credible interval because we're doing Bayesian analysis. Not confidence interval, credible interval. So it has a lower bound and an upper bound, and you can use that to see whether 0 is inside of it. And if 0 is inside of it, then you would say, well, there's not really evidence that this parameter deviates from 0. If 0 is not inside of it, then there's evidence that this parameter deviates from 0. For a variance, when you are doing Bayesian analysis, the credible intervals will never contain 0 because a variance cannot become negative. So don't get too excited here, you know, that, oh, like all my variance, like everything is random. Well, that's, yeah. Okay, what is, so we have these fixed effects here. And of course, one of the things that we might be interested in is looking at the cross-legged parameters and comparing their relative size. So especially so with negative affect and positive affect, we might be less excited about this, but when you are looking at males, like husbands and wives, you might be interested in like who is the driving force here? Like, you know, who's leading, who is lagging? So we are interested in comparing these parameters, the cross-leg parameters, as we are also when we just do cross-leg panel research. I want to know like which variable is causally dominant. I do it like this because of course we never know like unobserved variables, but that's the point of the research often. But to be able to compare those cross-leg parameters, we have to have standardized ones because otherwise it just depends on the scale of the variables. And even when the variables are measured on the same scale, like the same Likert scale or whatever, it doesn't mean that the amount of variance is the same. And that's the thing that we should be looking at when we want to compare the relative strength of relationships. And here, one other thing that you can think about is that if we have two people that have a parameter going from negative effect to positive effect of 0.3. But one person has a lot more variance in negative effect than the other one. It's not explaining the same amount of information or predicting the same amount of variance in the outcome variable. So that's another thing that we have to take into account. Standardization in multi-level models is a tricky issue. And that's why most programs do not include standardized results for multi-level models. Together with my former student, Noemi Schuurman, we published a paper discussing 4 ways of standardizing in multi-level models. So you can use the total variance, which is referred to as grand standardization. You can use the between-person variance, so that's the variance of the variables from the decomposition, just the between-person part. So the variance in the mu's, so that's between standardization. You can use the average within-person variance and use that to standardize parameters, or the within-person variance per person. And in the paper, we argue that it's most meaningful to use the last version, so to standardize per person, and then take the average of the standardized parameters, as this is what parallels what you would do if you just had a time series analysis, where you just have one case. You don't have any between-person variance. You just have the variance of this one person, and that's the variance that you use for standardizing your parameters. So that's what we argue in the paper, and I was happy to be able to convince Tiomir to implement this in Mplus. And it's now available for all multi-level models, so that's quite an achievement, I think. So then the standardized fixed effect is actually the average standardized within-person effect. Ugh, terrible sentence. What you get when you ask for STDYX is this kind of output. So it says within-level standardized estimates averaged over clusters. So clusters are the persons here. So it's standardized per person, and then the average of this is taken. And you see that we get the autoregressive parameter here for positive effect. We get the cross one from negative to positive and from positive to negative. And then we can compare those two to see whether one of them is much larger than the other. And here we see it's not really that much of a difference. And they are very small anyways. So. But this is what we get. We also get this correlation here. So it's the correlation between the, I assume it's between the innovations and not between the variables. So you can always ask Tiomir, you know, because he programmed it, so he knows. You also get the R square, so the within level R square averaged across all the clusters. So now you can see how much variance within a person is explained by the lagged relationships on average. But of course, this might be very different across individuals. So the part that I skipped before in the between-person output is with the with statements, so the covariances. So as you might remember, I allowed all the 6 random effects to be correlated with each other. So now, and then you get a 6x6 covariance matrix for this. Covariances are not so interesting, so it's better to look at the correlations. Again, you can get them by using the standardized results. And instead of representing this as a 6x6 correlation matrix for the younger and the older sample, I'm using a program QGraph by Sasha Epskamp in R. You can enter a matrix, for instance, a correlation matrix, and then plot this as a network. But I really want to stress here, for me, it's just a convenient way of representing a correlation matrix. I don't want to interpret this as a network where nodes trigger each other. It's in a way more comparable to cross-sectional data. But you see the means and then the 4 lagged parameters, and you see that this is the network for the younger sample and for the older sample. You see that the relationships are quite different for the two. The blue relationships imply negative correlations, the red ones imply positive, and then the thicker the line, the stronger the correlation is. So So this is one way to look at these kind of data and think about, okay, so what does this mean that, you know, the way that these variables are related to each other are different in younger and older people?